How's it going, everyone? Welcome to the third video of this semester. I'm going to do a couple things different today. First, we're going to start with a slideshow here to kind of talk about the Tidyverse broadly, and then we'll get into the R script. And when we do get into the R script, I don't have a pre-written script today. I'm just going to be doing some live coding. I've got some notes and an outline to show what all I want to cover, but once we actually start, it can be good to see how code is actually written rather than just scrolling over the final product. So that said, we'll just go ahead and get started here. So what is the Tidyverse? Bill and I have mentioned Tidyverse several times over the last few weeks, and the Tidyverse is essentially an ecosystem of packages that all play very nicely together. They all share a common design philosophy that is very human-centric. So its purpose is to make the entire process of data stuff, from the import to the tidying, transformation, visualization, modeling, communication, make every step of the data science, data analytics process to make that all easier. And so that it comes with a bunch of great packages, and when you load the Tidyverse, it will load all what's called the core packages, which is what you see here. But when you install it, it installs more than just these few packages or libraries. And today we're just going to be talking about 4 of even these core packages. But I just wanted to point out that, again, when you install Tidyverse, it will also install all of these libraries. So, but these are libraries that you're not going to be using day to day, unless you're working a lot with JSON files, or if you're doing a lot of web scraping and things like that. But all of these libraries also belong to the Tidyverse and share that same underlying design philosophy. But the 4 that we're going to be talking about today are Tibble, Reader, dplyr, and ggplot2. And so we've talked about Tibbles a bunch, and said that we'll get into what the difference is later, and so now that time has finally come. So Tibbles are data frames, but they're just better versions of data frames for a few reasons, and they do less, but in a good way. For one, they won't change variable names or types. We'll come back to that here in a couple minutes once we get over to Reader. Tibbles don't do partial matching, and Tibbles won't create row names. So as far as partial matching, what I mean is here, just as an example, I created a data frame with 3 columns. First column is called ABC, second column is called DEF, third column is called GHI, and here are the values, 4 rows on those 3 columns, and same thing as a Tibble, ABC, DEF, and GH and I as the columns. Well, with data frames, if you just call DF $A, it will return that first column because it uses partial matching. Whereas with that Tibble, if you try to call a column named A, it will tell you, hey, there's not a column named A. Same thing here. So if we just call df $G, it will return so many unintended consequences because it will return the values in that column, whereas the Tibble will not do that partial matching, which can cause problems. So, that's a good thing, that Tibbles won't ever do this partial matching thing. Additionally, Tibbles have an enhanced print option. So up here on top, I just called there's a data frame called Star Wars, and if I set it as a Tibble, this is how it displays. If I call that as a data frame, then down here is how it all displays, and you can see just scrolling down through the console that this is the actual output of returning the Star Wars data frame, whereas Tibbles return much more cleanly this way, and it will maximize that space. You can see where it breaks off columns and will list down at the bottom the columns that are cut off. If I had extended out my console and made it wider, it would show additional columns. If I scrunch that down in, it will break off additional columns and then just show those additional variables down here at the bottom. And so Tibbles, the Tidyverse makes, you could call it smart use of how you have your console set up. And so the way that it prints is a lot cleaner, makes it a lot easier to work with bigger data sets. Tibbles also allow for sequential evaluation. So what that means is that here, if I try to run, create a data frame where x is the values 1 through 5, and then y is x plus 1, the data frame will return an error, because when it'll evaluate x equals 1 through 5, but then when it says y equals x plus 1, it says object x isn't found because it can't operate on itself, essentially. It can't self-reference like that. Whereas a tibble, because it does sequential evaluation, it'll first evaluate this first value and set x as 1 through 5, and then when y says x plus 1, it knows to reference back to the x that it just created, and will then add one value to that, so it'll return x as 1 through 5, and then for y, it'll do each value of x plus 1. So that can come in handy in different ways that we may see later as well. And then talking about reader, so this is the library that we'll use to read in our data files, and you can either just read in the CSVs if you save them locally with read_CSV and putting in quotation marks, the file name .csv. Or we'll make use of reading in from URLs. Bill will usually, I believe, post the data sets on the class website, so it'll look something like this, and you just use that read_CSV, and you can put in the link in quotation marks, and that will read that data file. But earlier I said something about tibbles not changing column names, and one of the nice things about Reader is that it reads in your data as a tibble rather than as a data frame, which the read.csv is the base R CSV reading function. And so this will create data frames, whereas read_CSV creates tibbles. So here I have a strange data set that the column names are !@ $12334 ABCD, and :D, or big smiley face. If you use read.csv to read in this Excel file, this CSV file rather, it will change the names, because we talked about the first week and last week I mentioned that you can't have numbers as the beginning of your column names. Well, so base R, if you make that into a data frame, it's going to put this X in front of it. Same thing, you can't have special characters in data frame column names at all, so it just changes that first column to X period, 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 period. It replaces all special characters with periods, and it will lead with X's, and same thing here where it changes that colon to an X, whereas read_CSV, because it creates a tibble, and tibbles allow non-standard or non-syntactic column names, it will leave those column names as they are, and if it is one of these finger quote weird column names that wouldn't typically be allowed, it just wraps it in these backticks, which is not to be confused with the apostrophe. The backtick is to the left of the 1 key. And so same thing if it has a leading space in it, for instance, that's that non-standard thing. And so using read.csv can cause some problems when you get a data file from somebody and maybe they have the columns listed with numbers, or they use other special characters, or whatever the case may be. Read.csv will change column names, and read_CSV reader, this reader library, will never change your column names because it makes tibbles instead. dplyr is the workhorse of the data wrangling that we're going to be doing. Today we're only going to focus on a small subset of the variables, and that's filter, which is how we filter down the rows. Select is how we select columns or subset what columns are in whatever we're working with. Mutate creates new variables or changes existing variables. It mutates the values that are in the data frame. Summarize does exactly what it sounds like, and I'll note here that I often use the S in summarize instead of the Z. Either way works, the American English or British English. The author Hadley Wickham of Tidyverse is from New Zealand, and so they often use, you know, COLOUR for color instead of OR, and summarize with S instead of a Z, etc. But either spelling works. It'll recognize British American or British English or American English spellings. And then also group by does these other operations, but just with some sort of grouping variable. And then we'll talk a little bit about ggplot2, which that's the last time you'll hear me call it ggplot2. I'll just say ggplot. You just need to know that when I say ggplot, I am literally never, ever, ever talking about the original, you know, ggplot1. But rather, I'm just not going to call it ggplot2, and I'll just call it ggplot. But ggplot works off of the grammar of graphics, or specifically layered graphics, layered grammar of graphics, and we'll talk about what that means. But the real take-home point is that ggplot has intelligent defaults and you know, principal reasons for them that really make easy work of a lot of graphing stuff. I also want to point out that there are a lot of cheat sheets available for R packages, and not just the Tidyverse packages, but even, you know, just the RStudio itself, Reticulate, which is using Python with R, and then here just some examples of some of the Tidyverse packages, but they're usually 2 pages. They have a lot more information than you'll really need, so don't feel overwhelmed and like you need to, you know, study them and memorize all these things. But they are pretty good, especially like the ggplot for looking at things kind of at a glance. And so when in doubt, you can always just search for, you know, whatever cheat sheet, ggplot cheat sheet or dplyr cheat sheet, and see some examples of functions and things like that. In the spirit of Bill, who, as you may have noticed, really likes explaining where things got their names and talking about the people behind things, this fella here is Rene Magritte, who is a surrealist painter, and here are 3 of you know, his more famous paintings that you may recognize. But I really wanted to point out this one, The Treachery of Images. This is one of his famous pieces that it says in French, "This is not a pipe." And the reason that I'm pointing out Rene Magritte is because we make use of a library called Magritter, which is named after him because it is all about what's called pipes. And so these pipes, which is this % greater than % sign, make code a lot more readable and a lot more functional. And essentially what it does is whatever is on the left-hand side of a pipe gets piped through into the first argument of whatever is on the right hand side of the pipe. So for instance, if we have, you know, some variable, a pipe, and then mean, that is the same as putting mean open parentheses, variable close parentheses. So it's like piping that variable into the mean function. If we have a variable piped into round n equals 2, again, it pipes things into the first argument, so that is equivalent to doing round parentheses, that variable, comma, n equals 2, close parentheses. Pipes will help with making this code a lot more readable in a few different ways. One is that it avoids super complex nested function calls. I mentioned last week that we'll sometimes or even often use nested functions within functions, and when I said that, what I really meant was that, you know, if it's like a function within another function, and that's fine. But if you're nesting several functions this way, you know, this will very quickly become hard to read, especially because it's not, you know, just as clean as some short variable. It may be some much longer input, or each step along the way of these things have you know, multiple arguments that we want to put in. So the you know, some might have besides just the variable, it may have additional arguments in it, and then the round will have comma n equals 3 or whatever, and then so each one of these functions may have different arguments, to where when it's done this way, you know, it's going to take up the whole line, just one big continuous line of multiple functions, whereas when it's piped in, instead we just have the variable, we pipe it into the sum function, and then pipe that into the round function, and then pipe that into the print function, and it makes it real easy to sit and read through this sequence of operations. And it also, pipes keep us from having to store so many temporary intermediate steps along the way and clutter up our environment. So let's just say here, excuse me, we have we start with some data frame of 2,901 observations of 14 variables, and then we filter that data frame down, and we save that as data frame 2 that now has 2,382 observations. But then we subset those variables because we don't need all 14, so we just drop that down to the 5 variables that we need, and now we have df3. And then we create some two new variables based on the remaining variables and create df4. So now we're back up to 7 variables, and then we need to do another filter based on those 2 new variables that we created, leaving us with 235 observations of 7 variables, which we can see here. But we have to save those intermediate steps when we do it this way, which is kind of that base R way. And you see that over in our environment, we have now 5 data frames that we didn't need. We certainly didn't need df2, 3, or 4. We were just trying to get to df5. But if we instead used piping, then we would have that same data frame, 2,901 observations of 14 variables, and we just pipe that into some filter, and then take the output of that filter and pipe it into the subset function, and then take the output of that and pipe it into some function to create 2 new variables, and then take the output of that and pipe it into another filter based on those variables, and take the output of that and pipe it into our glimpse function. We can see that that still produces those same 235 rows of 7 columns, but over in our environment, we didn't create a new step and have to save an unnecessary data frame every step along the way. So making use of these pipes will help keep the environment a lot more clean, which is especially helpful if you're dealing with bigger data sets where you don't want to have to be storing these massive data sets every step along the way. And finally, pipes make it easy to add steps anywhere in your sequence of operations. So if this is what you're piping and you're doing something, then you realize you forgot something, or you want to add something or change something, it makes it easy to go in there and just throw in whatever new step in that sequence with an additional pipe wherever you need that thing to be. So all of this hopefully will make more sense as we get going here. But we'll go ahead and switch over to R. And like I said, today I want to do some live coding just so you can see how I approach things. And so for starters, we always start with our libraries up at the top, and the Tidyverse library will almost always be. In fact, I can tell you now, like, it will be at the top of every script. We'll never not load Tidyverse, and I already had it loaded apparently because it didn't, but I can restart just so that we can see. What happens when you load Tidyverse is it will come up with this. And I wanted to point out, whenever you're loading your libraries, make sure that you're paying attention to your console, because it will give you useful information. For instance, here it will tell us what these conflicts are, and it says dplyr : filter masks stats : filter. What that means is that the stats is the base R library. And so in the base R library, there is a function called filter, and in the dplyr, which we just loaded, it also has a function called filter. So when this says dplyr filter masks stats filter, what that means is that if you just tell R filter something, it needs to know which filter you're talking about. Do you mean dplyr filter, or do you mean stats filter? Because they're 2 separate functions and they don't work the same way. Well, now we know that if we just say filter, then R will assume we mean dplyr filter because that is masking stats filter. If we did need to call the masked function, the stats filter, then we would have to explicitly say stats : filter. And now R would recognize that we were talking about this filter here and not this filter over here. So same thing here. If we just use lag, R is going to assume that we're talking about dplyr lag and not stats lag. So you need to pay attention to those kinds of things whenever you're loading your consoles, because well, first of all, like, this idea of masking functions is one reason that we don't want to unnecessarily load just tons and tons of libraries, because you're bound to run into conflicts like that. And so sometimes I'll make use of what I call a one-off function. So for instance, if I use make up some, we'll say that there's some library called pkg, and then some function called sum.function. So this is from the pkg library. There is a function called sumFunction, and if that's the only function from that library that I'm going to use for this whole script, then I'm not necessarily going to load library pkg, because then it loads all of pkg's other functions, and it might conflict with something that I want to use. So instead, I'll just use this explicit notation, and I'll also use this notation occasionally just to remind you all of what packages specific functions come from. So when you see this, you'll know that, oh, sum.function is from the package library, but after that, all you'll see used is the actual function itself and not the reminder of what library it's from. So that said, just glancing over here at some notes. Another thing I want to point out today is that we are just kind of scratching the surface of these Tidyverse things, and that there are other versions and some nuanced things that we'll get into as the semester goes. But at least after today, you should be able to do the bulk of your data manipulation and such. But so I'm going to start with some built-in data instead of reading in a data set. So R has a bunch of, and if you look at data sets, R has a bunch of built-in data sets that are just already available. And then there are other, oftentimes different libraries will also come with built-in data sets that are good for illustrating particular functions within that library. So today we're going to look at one called mtcars. And so if we put the question mark, it'll pull up in the help documentation and tell us what it is. So mtcars is the motor trend car road tests from 1974. There are 32 observations with 11 variables, where we have, mpg is miles per gallon, CYL is number of cylinders, etc. So if we just look at mtcars, we'll see that that's what we have. But earlier I said something about Tibble not having row names and that being a good thing. Here is an example of this. If you look in mtcars here, you see that we have all of our miles per gallon, cylinders, displacement, etc. And then our car names over here, but notice it doesn't have a header. And that's because if we look at our structure and just pipe that mtcars into the structure function, which again, that is the same as writing structure mtcars. When we run that function, we can see that that those car names are gone. That's not actually a row in the data or a column in the data. Rather, these have row names of what the car's names are. Now, the reason that that's not good is because that's useless to us. If the car's names are not in the data itself, we can't use those. We can't reference those. So instead, it would be much better to just have the rows numbered and then have an additional column that has all the different car names in it, so that we can actually have that as usable data. So instead, I'm going to take mtcars and I'm going to use a function as Tibble. And because I want, we can see here there's an argument called row names, and so if I put row names equals, say, car.name, what it'll do is it'll create a Tibble, and it pulls those row names out of, well, the row names, and puts it into the data set. So I'm going to take this now and store it as an object called cars, and we can click on it there, and we can look up here, and we can see that now we actually have a column called car.name that has those car names in it. So now that we have our data set, let's start to take a look at some of these dplyr functions. So first, let's look at select. And so again, our select function, what it does is it chooses what columns are available in some data frame. So if you recall, before, what we talked about is if we wanted to subset this cars data frame using the base R method, we use these brackets and we say cars, and we want all rows, so we leave that first place blank, and then over here in the columns we have to select which columns we want. So say we want MPG, we want HP, and we want AM, which is miles per gallon, horsepower, and automatic versus manual transmission type. And when we run that, it will return those three columns. Or alternatively, we could run instead of the MPG, instead of running it by their names, we could say in the concatenate, 1, 4, and 9, and it will, I guess that's 2, 4, 5, and 10, because I forgot I added the other name. And so that's how you would subset this in base R. Instead, using select, it's a pretty straightforward function. You just have to put in whatever variables you want to keep. So if I just say select, I'm going to pipe cars into this select function until it's a select MPG, HP, and AM. And when I run that, it will return those three columns. And call me crazy, but this seems a lot more straightforward than, say, this approach. Beyond that, the select recognizes the colon as meaning all of the variables between, or a range of consecutive variables. So what that means is, again, I'm going to pull up cars just so we can see what all of the variables are. And let's say that we want to select the car name through the cylinder, car.name, cylinder, and it will select those three columns. Moreover, you can do groups of consecutive things. So if I just add a comma here and say car name CYL, and then say we want to do VS carb, and so now it'll pull all the variables between car name and cylinder, and all the variables between the engine shape, V shape versus straight, and number of carburetors. So from there, we can also choose, we can also select which variables not to keep, because maybe sometimes instead of selecting a few variables that we do want to keep, it's easier to tell it which variables we don't want to keep. So for instance, let's just say here, we don't want to keep this displacement, well, we'll just start there. So we don't want to keep the displacement variable. We can say minus DISP, and it will recognize that minus as meaning the complement of, or not this. So select all of cars, but not this DISP displacement variable. Or the exclamation point works the same way. So if we use the minus or the exclamation point, it will exclude whatever variable it is that we're talking about. if you're wanting to exclude a range of variables, the only difference is you put the range inside a parenthesis. So if we say not, so exclamation point, and then in parentheses say HP colon VS, it will select all of the variables but not the variables between HP and VS. And then finally, you can put all of these things together. So let's say, again, let's take a peek at the full data set. And let's say that we want to select the first column, car name. We want to select HP to PSYC, or well, let's say HP to AM, but not PSYC actually. And when we run that, we can see that it selected car name and it selected HP through AM, but left out that PSYC variable. So this select function makes it very easy to select whether it's individually, a range of consecutive variables, or using that exclamation point or minus sign to say to not select something in particular. Now, I'll also just point out that notice how throughout all of these things we only have this one data frame down in our environment still, so we haven't subset and kept them as that subset, which is good. But let's just say that you did want to have this as its subset, and so if we wanted to save this particular subset here that we just created, all you have to do is come back up here and throw in an assignment arrow, and we'll call it cars subset. And when we run that now, we can see that we have a new data frame down here in our environment called cars subset, which is the subset of the cars data frame that has car name, HP through AM, except not that PSYC variable. So from there, let's talk about the filter. The filter function. So filter does exactly what it sounds like. It filters your data based on some logical test or tests. It will return whatever evaluates to true for anything that you put in it. So what does that mean? If we take our cars data set, full data set, and we want to filter down, and let's just say that we want to keep all cars that have that are greater than 20 miles per gallon for their fuel efficiency. All we have to do is tell it filter MPG is greater than 20, and it will return the 14 values that are the 14 cars that are greater than 20 miles per gallon. If we want multiple filters, so we want all cars that are greater than 20 miles per gallon, but say we also want just the automatic transmission, so where AM equals 0. AM equals, remember that for logical tests you have to use two equal signs for the equivalence. So here just filter all cars where MPG is greater than 20 and where AM equals 0. And we can see that there are 4 cars that meet both of those criteria. And from there, we could also, if we wanted to, go even further and say also we only want where gear is, the number of forward gears is 3, and we now are down to 2 values of that. So these filters, you just keep adding whatever logical tests separated by commas. From there are more functions that we can get into as we go, but say for instance there is, if we want to see everything that is where the miles per gallon is between 10 and 20 miles per gallon, we could say filter between and then tell it where miles per gallon is between 10 and 20, and it'll work there. This not necessarily something that you have to know right now, just now showing a few other nice features. You could do instead of, maybe you don't have a hard set number. Maybe instead what you want to do is you want to see which cars are kind of outliers, or in the upper half of something. So you say if you want to filter where miles per gallon is greater than the median of miles per gallon. And so now it will only return the cars where, if you do a median split on miles per gallon, it's only returning the 15 cars that are greater than that median value. Or you could say, if you wanted to do the mean miles per gallon plus 1.5 times the standard deviation of miles per gallon. So now we're saying, filter, only show me the rows where the miles per gallon is greater than 1.5 times the standard deviation of the mean of miles per gallon. So you can filter based on any sort of logical test that you want, and as long as it evaluates to true, that row will be retained in your output down here. Once again, though, notice that doesn't save down in your thing, which is, again, good. You don't necessarily want to. Even if you were wanting to filter down, normally you're just wanting to filter down for some specific operation. You're wanting to filter down to then look at some summary statistic, or filter down to create some model or something like that. And so you can use that filter and get that summary statistic or create that model without actually storing that subset or filtered data set over in your environment. And if that doesn't make sense to you, it will as we actually get into doing some of these things for real. It should become apparent what it is that we are talking about there. So the next thing that we'll talk about is mutate. And so what mutate does is it creates variables, or it can change variables, but as a general rule, we don't want to change variables. We want to create new variables. One of the great things about Tidyverse is it makes it really easy to not mess with your original raw data, which you don't want to do. Anytime that you're working with things, when you're working with data, the more that you save over existing data or change existing data, the more likely it is that you're going to end up having a problem. And so a much better practice is to always create a new variable or a different variable, but leave your raw data as it is. Leave it unaltered. And we'll talk more about that as the semester goes along. But for now, let's look at this mutate function. And let's say, so we're going to take our cars variable, and first let's just say, so when we look at cars, it gives us, we have 12 variables, a 32 by 12 table. So if we just want to create a new variable, we'll say mutate, and we'll call it new var equals a. And that's just going to create a new variable and set every value to a. So instead of that, let's say that we want to mutate and create let's say for whatever reason, we want to look at the product of gear and carb and call it something. So we can say we're going to pipe cars into mutate, and we tell it something equals gear times carb. And when we run that, we can see that we have this variable called something that it just multiplied this gear times the carb. 4 times 4 is 16, 3 times 1 is 3, 3 times 2 is 6, etc. You can do more useful things with this. So say, for instance, we're not in America, so we don't use miles per gallon anymore, and instead we want kilometers per liter. So the conversion from miles per gallon to kilometers per liter, so we'll call it KML for kilometers per liter, equals, and that would be your miles per gallon divided by roughly 2.35. It will give you a close approximation, and so we know that the Mazda RX-4 has 8.94 kilometers per liter at 29 or 21 miles per gallon. And I want to take a brief sidebar here to introduce a quick function called if-else, that if ever you're needing to like dichotomize something, an easy way to do it is with this if-else function. Later we'll talk about a tidyverse approach to using if-else, especially when it's multiple if-else statements. But let's just say, for instance, we're looking at our miles per gallon, and let's say if-else miles per gallon is greater than, let's call it 18. So if-else logical statement, output if true, output if false. So this is what the if-else statement, how it's structured. You have some logical statement and then two values. One, what the output will be if it's true, and then what the output will be if it's false. So if if the miles per gallon variable is greater than 18, we'll say high efficiency, and then comma, and then quotation marks, low EFF for efficiency. So now what this if-else statement says is if the miles per gallon variable in the car's data frame is greater than 18, then output high F, else output low F. So when we run that, we can see that it's going to return a vector of a bunch of either high F or low F. So now if we put that in conjunction with our mutate, we could say cars, and if we want to create a variable called fuel EFF for efficiency equals, and now we'll just put in that if-else statement. We have now created a new variable called fuel EFF, where if it's greater than 18 miles per gallon, it's labeled as high efficiency. If it's less than 18 miles per gallon, it's rated low efficiency. And we could even go further than that, and if we wanted to do, say, a mean split, we could say the mean of miles per gallon. So now instead of using 18 miles per gallon as the cutoff, anything that's greater than average is going to be called high efficiency, and anything that's lower than the average is going to be called low efficiency. And I said that this can be used for not just creating variables, but also changing existing variables. So if we want to, say, change this horsepower column, and for whatever reason we want it to be a character vector, we could just say horsepower equals as dot character HP, and now you can see that it is returning horsepower as it just changed horsepower to, instead of it being a double or numeric vector, it's now a character vector. Or if we wanted to divide it by 10, HP divided by 10, you can see what used to be 110, 93 is now 11, 9.3. So that's how you change existing variables. But again, just to point out that that this is not saving these variables. So here we mutated to create this new variable called fuel efficiency, and but again, when we look in our data frame, it's not down here. If we want to save this newly created variable, again, we come back up to the top, and we will just have this entire pipe chain. We add this assignment operator, and we're going to store this back over the car's data frame. And when we do that, we now have 13 variables in our data frame, including that fuel efficiency column that we created. So the next thing that we're going to get into is using summarize and group by. So again, summarize is exactly what it sounds like. It's going to collapse across rows to create summary variables. So say we want to summarize the mean miles per gallon for all things. We could say to summarize mean MPG. And it will give us like 20.1 is the mean miles per gallon across all 32 of these cars. And you see here where it actually, this outputs a tibble, and the column name is just whatever function you put in. But you know that can become a problem, and it might be easier to just include column names in the function itself. So we could say that this is m.mpg equals mean MPG, and that's what it's going to name the column. So let's say we want the mean, we want the standard deviation of the miles per gallon equals SD miles per gallon, and we also want the count, n equals n. So when we run that, we can now see that the mean miles per gallon is 20, the standard deviation of miles per gallon is 6.03, and there are 32 of these. We could also, if we wanted to, say, min MPG equals min MPG, and you could do max, etc. All of those summary functions, and you can just add on, whatever it is that you're needing there. But we may not necessarily care about overall. I mean, when you look at these, it doesn't really seem fair to compare just like the average. I don't think that's going to be very representative when you look to see that we have some 6-cylinder, some 8-cylinder, 4-cylinder. We have manuals versus automatics, all sorts of things. So instead, let's say that we want to look at these same statistics here, the mean and standard deviation and the count, but we want to do that by cylinders instead. So we come in here, and I just copied and pasted, and all I'm going to do is I'm going to add a group by, and let's group it by cylinder, CYL, add another pipe. And so now we're taking this cars data frame, we're going to pipe it into this grouping function. We're going to group it by cylinder and then pipe it into the summarize function, where we get all of these statistics based on grouping by that cylinder variable. So when we run that, we can see the 4 cylinders, here's their mean standard deviation. There are 11 of them, and here's the minimum miles per gallon. For the 8 cylinders, 15.1 mean, 2.56 is the standard deviation. There's 14 of those, and 10.4 is the minimum. So, but what about if we wanted to change that? We could, well, just for example, I'll copy and paste instead of just changing it. And so if we want to look at the manual versus automatic, again, the automatics are zeros. So for the automatics, here's your mean, standard deviation, n, and minimum. And for your manual, are those statistics. If you want to group by 2 things, you just separate it by a column, a colon, and we can group by transmission type and the number of cylinders. So here are our automatic 4, 6, and 8 cylinders. Then here are the manual 4, 6, and 8 cylinders. And notice how it groups them in the order that you have these grouped in. So if I switch these around and do CYL, AM, it will now do the 4-cylinder automatic versus manual, the 6-cylinder automatic versus manual, and then the 8-cylinder automatic versus manual. So this makes it very easy to quickly tabulate across any sort of thing. So if you were trying to get your counts of how many, a breakdown of cylinder by transmission types, you know that you have 3 automatic 4 cylinders, you have 8 manual 4 cylinders, you have 4 automatic 6 cylinders, you have 3 manual 6 cylinders, etc. So that's how you make use of the summarize function. Then, you can string all of this together. to put it all together, let's say that we have our cars data set, and what we want to do is we want to mutate. We need to create some new variable. Let's take a look at this. And for whatever reason, let's just say we're interested in some weird variable that is, the weight, the product of the weight and the quarter mile time. So we can mutate to create those, and then let's pipe that into a filter. But we only want to see the high fuel efficiency. So we'll say filter where fuel EFF equals high EFF, and then we can pipe that through. And we don't need all of these variables, so let's keep car name. We're going to use select and keep car name through AM, and then we want to group it by, and I guess, technically if we're just doing summary statistics, the select, if we run through there and just to take a look at where that is so far, you can see where that's selected down to. But then let's group it by cylinder, and summarize max equals max HP. And so once we filter, once we take our original data frame, create this weird variable, in fact, let's say max weird instead of HP, because that makes more sense since we created that variable. Take out that select. So we created this weird variable that is, the weight times the quarter second or quarter mile time, filtered only looking at the high efficiency vehicles, broken down by cylinder. That gives us only 4 and 6 cylinder, and the max variable for, or the max values for that weird variable that we created is 72.1 and 62.5. So you can just chain together all of these different things. Finally, the last thing that I'm going to mention here, just because I hadn't mentioned it before, is reading in data. Using reader, and this is real simple and straightforward. So let's just say that we have some link. I'm going to copy and paste a link here, and it's to some data that Bill has hosted on a class website. One thing that you can do is just you read_CSV and then put that link in your quotation marks, and when you run that, it will it'll read that data frame. But notice that just running read CSV doesn't do anything. You have to store that as an object. So we'll call this wages. And we now have this data frame called wages, or rather this tibble called wages. And the alternative you can see here over in my over in this folder in my working directory, in my week 3 folder, I have a file called wages. So I could do the same thing if I do read CSV and just wages.csv. That's going to, instead of reading the link, it's going to read that local file that's in my working directory folder here. I'm going to suggest always saving that file from the class website instead of using the link directly, just because it's possible that this link changes, whether the university changes their URL structures or Bill just deletes that, this particular folder, changes whatever the file is, removes that file, whatever the case may be. If down the road you're coming back to look at your script to figure out how to do something, and you can't access the data because you don't have the data, you just got it off the internet, but it no longer exists in that place on the internet, you're kind of out of luck. But if you save that file and do it locally, then you always have that file and can always read it. So the next thing that we want to talk about is ggplot. And to talk about ggplot, I'm going to go back to our cars data set. And so the first thing that we're going to do to create ggplot, I'm going to start kind of from the middle, and then we'll go back to the beginning at the end. So to create a ggplot, you first have to give it some data. So we're going to tell it that the data equals cars. It's this cars data frame that we're looking at. So I'm going to tell it ggplot data equals cars, and it will initialize the ggplot. But you see that there's nothing on here. It's just a blank plot because we haven't given it any information whatsoever. When it comes to the grammar of graphics, there are it's called geomes, geometric shapes. So that's, what do you want on your plot? You need something visible. Well, in this case, let's say we're trying to create a scatter plot, and we want to plot, miles per gallon against the horsepower. So we need to tell it that we want to add a layer. If you recall, I said that this is layered graphics based on the grammar of graphics. And so we just build successive layers. So we're going to take this ggplot and add this plus sign, which tells it to add another layer. So then we're going to come down to this next line, and we're going to tell it to add a geome point. And points are just the dots. Now, one thing that you need to understand ggplot is this idea of something called aesthetics. And what an aesthetic is, or AES parentheses, aesthetics are when you're pulling some information from the data set. So in this case, the information that we're pulling from the data set is our x and y values. So we want to tell it our x equals mpg and our y equals hp. And so now it will create this very, very basic scatter plot for us. Now, to help kind of better understand what the aesthetics are, let's say that you wanted to change those dots to make them red. You could say color equals red, and there you go. You have red points now. Or we could say size equals 3, and there we go. We now have bigger dots than we did. But if you instead, let's say, instead of just making it all one constant color, we wanted to break down the color based on high versus low fuel efficiency here. So we have that fuel EFF variable. That is coloring it based on information in the data frame, which means that it is an aesthetic. So instead of color going outside of the aesthetic over here, we would put that inside the aesthetic and say color equals fuel EFF. And now it will have our low efficiency vehicles over here and our high efficiency vehicles over here, broken down by that color. Same thing if we wanted to do our size changing based on high versus low fuel efficiency, where we could say our high efficiency are small dots, our low efficiency are big dots. So if you're pulling information, if you're using information from within the data frame to change something about your figure, that is called an aesthetic, and it goes inside this AES parentheses. If it's a constant and it's and what's in the data doesn't matter, it goes outside of that aesthetic. So then there's another, but let's say that instead of just coloring it based on the fuel efficiency, we want two separate plots. We want one plot that shows the high efficiency and one plot that shows the low efficiency. That's where we'll facet this particular graph. And so we'll use this thing called facet grid. And facet grid, just like how our brackets are, row, comma, column, facet grid works the same way, but it's separated by a tilde. So if we are only faceting by one thing, you use a period as a placeholder. And so if we want a column of high and low efficiency, we could put a period, tilde, and then fuel EFF. And it will facet to give us two columns, one that's our low efficiency vehicle and one that's our our high efficiency over here and our low efficiency over here. If we switch that around, and do fuel efficient tilde period. Now this will break that down into, it'll give us rows where one row is high efficiency and the other row is low efficiency. Or if we wanted to break it down two ways, we could do that. And we could say break it down by fuel efficiency and cylinder. So now we have our columns are the cylinders, 4, 6, and 8. And our rows are high efficiency versus low efficiency. Or an even better example, let's look at automatic versus manual transmission. So here we have our automatic 4 cylinders, automatic 6 cylinders, automatic 8 cylinders. So using this facet is how you break these things down into separate plots. Now, there's also, let's go back here, because this is, again, these have generally good defaults. One of the defaults that I don't particularly like is the theme, or kind of this coloration of the background. But I wanted to point out that there are several. If you add this plus sign to add a new layer, come down here, and you're going to say theme underscore. You see that there are a bunch of like pre-made themes. So let's look at what happens if we add theme underscore BW. It changes our plot to look like that. If we add theme classic, it gives us this clear background with no grid lines. If we change that to theme dark, it will give us this dark theme. And so you can go through and play with all of these different themes. My go-to, I almost always go with theme classic just because I want the clean background, and then later in the course I can teach you how to add in like your own grid lines and specify, because that's what I like to do. I like to start from a clean slate, and then if I need grid lines and things, I'll add them manually myself, and I use this so much that I actually have a quick button programmed into my computer that just automatically adds ggplot and automatically puts the theme classic in for me. But beyond the geom points here, you know, we might want to look at the at histograms. So let's say we want to add ggplot, and we got to tell it our data equals cars, and then let's add a layer and tell it that we want a geom histogram. And if we just try that, it's not going to work because it's going to tell us that we need an aesthetic. So in this case, we need to tell it what we want a histogram of. So let's say we want a histogram of miles per gallon. So x or y equals miles per gallon. If you do it as an x, it will instead, you know, just do it this way. So depending on which way you want it. But you notice that with histogram, it tells you, it gives you this warning down here that says using bins equals 30, pick a better value with bin width. This intentionally was designed where no matter what the data is, it will always give you 30 as the default number of bins, and will then make you change that. And what that means is that if we come up here, because you see how this is, we want to group these things. Bill kind of talked about this a little bit last week, but we want to group these things by something a little bit more sensible. So we got 10 to 30 miles per gallon. Let's say we want our bin width to be, we'll start with 5. So now there is everything that is between the base and going up, you know, 10 miles per gallon, or by 5 miles per gallon, and then the next bar is everything that's within the count of that's within that next bin of 5 miles per gallon, and then the next bin. So 5 looks a little bit much. Let's change that down to like 2.5. That's not particularly pretty either. 2 miles per gallon is a little bit too small. 3 miles per gallon, etc. So playing with that bin width is going to change how the how wide those bars are and what values, what observations get grouped within any particular count. Alternatively, with histograms, Bill used the hist, and you could say cars $MPG. And it's going to give you that same kind of default, but again, this is not a ggplot, and literally if you are wanting to customize this base R plot of histogram any at all, you'll have to look it up, because I cannot tell you anything beyond, well, if you put in the variable, this is how it turns out. So you can change the bin width up here, and then there's also, just know that any of these, if I want to add on my theme classic onto that, clear up that background, and just know that any of the customizations that you want to do for anything else, which we're not getting into this week, so I'm already running over an hour, but any of the customizations of ggplot that you then wanted to apply to this, you could, as far as changing the color, changing the labels, changing grid lines, changing anything about this graph, essentially. Same thing if you wanted to take this and facet it, you could throw that into facet grid, and let's say that we want to create columns, not rows, so we'll say break that down by AM to see the miles per gallon of our automatics versus our manuals, etc. The last thing real quick that we're going to do is look at our box plots. And so, as you can guess, we have to start by initializing a ggplot and telling it that our data is cars. And then we're going to add the plus sign to add a new layer. And we're going to tell it that we want to add geom box plot. And if we run that again, it's going to tell us, like, hey, we need some sort of aesthetic. What is it that you're wanting to make a box plot of? So in that aesthetic, our aesthetic, let's say again, we want to make a box plot of miles per gallon. So when we create that box plot of our miles per gallon, it'll create it this way. Then say we want to facet that by, but this time we want to make one column with different rows. So let's facet it by cylinder, and we'll do cylinder tilde period, and it will create different box plots based on 4, 6, or 8 cylinders. If we wanted the box plots going the other way, we could call this Y. But see, now having it, if we're using it as vertical box plots, it doesn't really make sense to have it broken down by rows, and instead we'd want it broken down this other way. So we'll throw the period and tilde in front of it, and now we have 3 columns with those vertical things, depending on whether you tell it X or Y for those box plots. And again, if we wanted to clean that up or just change it and have say theme gray, we can do that, or theme BW for black and white. We can change those themes, we can change our colors, we can do any of those things. But most of the time when it comes to histograms and box plots, that's going to be during the kind of exploratory data stuff. You're not really going to be doing box plots and histograms of your analyses, generally speaking. That's more so just during that exploratory phase, and there are still better ways of doing that even that we'll talk about. So don't worry too much about the customization per se of this box plot and histograms. Really, it's once we the geom points that we'll be doing a lot of customization in, and once we start plotting out our various statistical models and things like that, is when we'll get into the really cool and fun stuff. That said, I'm going to wrap up this video. I believe that we've covered everything that we'll need. Short of, I apologize, I just realized one thing that I skipped, and let me come back up here and add it, just kind of a general note at the top. That there's column names, and if you do column names cars, it will output what all your column names are, or if you do cars, you can pipe that into call names. And or say you have your subset and wanted to see, well, what are the column names of our subset. We can print it out this way because this is a function that will be useful for the exercise. So I'll come back to this. I'm going to modify this script a little bit, so there will be a note here that won't make sense until you get to the end of the video. But also I will put a link down here at the bottom. That's to a 20-minute ggplot intro video that I made a couple years back that might also be good to watch if what I've said here doesn't make sense. That other one was it goes a bit slower, and I wasn't trying to rush just because I'm already running so long. So that said, I'll have a link down here at the bottom of the script to another video on ggplot if you want to watch that. That one's about 20 minutes. But outside of that, that covers the gist of what we need for this week at least. And we will definitely, we'll basically be continuously learning about ggplot, and every week I'll be introducing you pretty much to something new about it and expanding from there, because we haven't even scratched the surface on the possibilities of ggplot here. But that said, that wraps up this video, and I will see you all later.